attending. So today I'll be discussing some recent work that I have done in terms of generalizing the notion of Kähler metrics with Poincaré-Type asymptotics along a divisor. So I'll first do sort of a quick recap of the basic tools in Kähler geometry and discuss what exactly I mean by a Kähler metric of Poincaré-Type, and then why perhaps we might want to generalize them, and what I have done in terms of generalizing them, and hopefully further directions that I can take these generalizations, or anyone else can if they're so inclined. So the basic setting of Kähler geometry, the notation I'll be using throughout this, I'll have a compact Kähler manifold X. Being Kähler means that we have three compatible structures. So one of them is this endomorphism of the tangent bundle J, which squares to minus the identity. So it basically is a generalization of multiplying by I. And I have a non-degenerate two-form sigma, and I have a Riemannian metric G. And the endomorphism J gives you a map from tangent bundle to tangent bundle, and G will give you a map from tangent bundle to cotangent bundle via duality. Same thing with a non-degenerate two form, and the commutation of this diagram with the yellow arrow tells you that these all agree with each other. And being Kähler involves also an integrability condition, which for my purposes is going to be that J actually arises from a holomorphic atlas on the manifold. So I have holomorphic coordinates everywhere, and the two-form sigma is actually a closed two-form, so it's a symplectic form. Another way you can think about it is we can choose charts on X such that the transition functions for the tangent bundle are actually they preserve a UN structure, and we can choose coordinates such that it does so to first order. But another way of simplifying all of that is to just say that the complex structure J is parallel. So there's plenty of ways you can characterize Kähler manifolds, but this is the structure that I'll be working with. And the tools that all sort of fall out from the complex geometry and being Kähler, one of them is that if you complexify the tangent bundle, so just tensor with C, then the complex structure actually gives you a splitting into eigenbundles, I and minus I, which we usually notate as T10 for the I eigenbundle and T01 for the minus I eigenbundle. And you can do the same decomposition on the cotangent bundle, and that'll give you a whole decomposition of the forms, the differential forms on X once you've complexified, which is what I have here now at the top. So the complex K forms split into what we call PQ forms, where we have P holomorphic pieces and Q anti-holomorphic pieces. And another consequence is that we get a few different differential operators that will be pertinent for our discussion. So one of them is the splitting of the de Rham differential D into del and del bar, which basically take holomorphic derivatives and anti-holomorphic derivatives. And you can then create an entire complex using these differential operators to establish what we call Dolbeault cohomology. And we also can just stick with real valued things, which is where this DC operator comes into play. It'll just make things a little easier for me to write things in terms of D and DC than del and del bar. So DC is defined by taking our de Rham differential D and twisting it with the almost complex structure J. And if you're more familiar with the del bar world, then we have a relationship between DDC and del bar. And one other operator that's a little less common, but will be pretty important here, is this sort of script D operator that I've written. this takes two derivatives of functions, and what we do is give it a function. It'll first take del bar of that, which will give us a 0, 1 differential form. And then we sharpen this with respect to our metric, which will take a 0, 1 differential form to a 1, 0 vector field. And then we can take the Gobot operator of that vector field. Okay. So one other consequence in the compact Kähler case arises from Hodge theory. I'm just including this because I will use harmonic forms later for perturbation reasons. So this decomposition on the differential forms actually extends to the cohomology in the compact Kähler case, so that the kth de Rham cohomology with complex coefficients splits into these PQ cohomologies. And in particular, this happens for harmonic forms as well. So a harmonic K form will split into a sum of harmonic PQ forms. And one of the sort of important tools that we use is the fact that Kähler metrics actually locally look like DDC of something. So locally, they're always complex Hessians, essentially. And an example where this is actually globally true that we'll be using a lot here is on the punctured disk. So I've drawn just a little slice of it because it's infinite in both directions. But there's a function that we can write on the punctured disk whose complex Hessian gives us a very nice Kähler metric of constant scalar curvature. So if we take the standard coordinate z on the disk, and then we take log of minus log of the norm squared of z, then this gives us a sort of log polar coordinate that we can use. And then if you take the complex Hessian of that, you arrive at what we typically call the standard cusp metric on the punctured disk. And we can compute the scalar curvature of these Kähler metrics. You can either do this the old-fashioned way by writing it as a Riemannian metric and going through all that process, but in Kähler geometry, we have some tricks we can use to define the scalar curvature using not just the Ricci tensor, but we can actually twist the Ricci tensor by inserting the almost complex structure into one of the slots on the Ricci. So we'll take it from a symmetric 2 tensor to an antisymmetric form. And we can wedge that with our Kähler form sigma to effectively take a trace of it as we would for just a Riemannian metric. And if you define your scalar curvature as the function which satisfies this second from the bottom equation that I've written here, then you can compute the scalar curvature of the metric that I've written, and you should find that it is constant scalar curvature -1. Okay, so that's the basic element of Kähler geometry I will use. And to define a Kähler metric of Poincaré-Type, essentially we're going to be looking at Kähler metrics which in one direction look like this punctured disk, and then the other directions are just a nice smooth guy. And the best resource for the details on these Poincaré-Type metrics is a paper by Auvray, which I've just written out the title of here, The Space of Poincaré-Type Kähler Metrics on the Complement of a Divisor. He has multiple papers, which are great resources for Poincaré-Type theorems, but this one sort of lays out all of the basics. So to define this, we're going to introduce an ambient manifold M. So M is one complex dimension larger than X, so that X sits as a complex hypersurface inside, and M is going to be equipped with a Kähler metric, sort of a background smooth Kähler metric omega naught. And our picture is that X rests as a hypersurface, and the metric we have has all of these cusps that I've done in green. As we get closer and closer to X, we are this normal direction from X looks like this puncture disk model. So another way to think about it is that we're sending this hypersurface X metrically off to infinity in some way. And to be more precise about the definition, we will say that a Poincaré-Type metric on the complement of our hypersurface X in M, it means that for every point in the hypersurface, we can pick holomorphic charts about the point, which have a defining coordinate for X. So here I'm thinking of one of my holomorphic coordinates in U as being coordinate Z, the zero set of which defines X there. And on this coordinate chart, we can write out this metric here, which looks like the standard cusp metric that I wrote above, plus just the restriction of my background metric to the hypersurface. And I want this Poincaré-Type metric to be quasi-isomorphic or comparable at all derivatives with respect to this sort of local model Poincaré-Type metric that I have here. So basically, near the divisor, I can always write it, or I can always find coordinates such that my Poincaré-Type metric looks like or is comparable to this metric here, which is initially a pretty loose characterization, though we'll see that it tightens up if you put just a few analytic restrictions on this. So that's the idea of a Poincaré-Type metric in general, but to parameterize these things, it's very helpful to introduce the notion of a class of Poincaré-Type metrics. So a metric omega is a Poincaré-Type metric in the class omega naught, where omega naught was a smooth background metric on all of M. Basically, it means that omega differs from omega naught by ddc of some function, but this function needs to be comparable to that earlier function tau, this log polar coordinate that we have in the coordinates that we're working in. So basically, we want things that look like something smooth plus ddc of this log polar coordinate, all within a certain error that we're comfortable with. And when we write a Kähler metric as a complex hessian of something, we call that something the Kähler potential. But when we are writing a Kähler metric as another Kähler metric plus ddc of something, then we'll call that other something a distortion potential, terminology from Calabi, at least. And just looking at this diagram, we might ask, okay, so this is the definition of Poincaré-Type metric. Are there like restrictions on the existence of these things? If you have a complex or a Kähler manifold, can I just remove any hypersurface or in particular normal crossings divisor? Can I define one of these things? And the answer is yes. So these Poincaré-Type metrics always exist given the appropriate setting, because there's an analog of the distance from a hypersurface that's actually a globally defined thing. So a hypersurface in a complex manifold can be defined as the zero section of a particular holomorphic line bundle, or not the zero section. It can be defined as the vanishing locus of a section of a holomorphic line bundle on the entire manifold M. So here I've notated the line bundle is O sub M X, and that is from the divisor line bundle correspondence complex geometry, the line bundle that gives X as the zero locus of a section S. Okay, so we have the section S, it vanishes on X, and we can equip our line bundle with an Hermitian metric that we can just make small enough such that instead of having log of minus log of norm z squared, we can now just plug in the Hermitian norm of our section. So this is going to behave essentially the same way as this tau in our coordinates as we're close to the hypersurface x. So we just make this small enough so that it all is well defined, and then you can add that onto your background metric omega naught, and you have a Poincaré-Type metric. You don't have a whole lot more information than that, but it is always, you can always just make one of these things. And why would we care about these Poincaré-Type metrics in particular? Well, a few nice properties they have is they're complete, and they have finite volume, and you can also compute their average scalar curvature using topological invariance. In the compact Kähler case, you can compute the average scalar curvature using the first term class and then the Kähler class that you're working in. Here it's similar, but you also have to include the first term class of this line bundle that I've defined. But there's a way to do that. So you can study them in ways very similar to the compact Kähler case. You mostly just have to make sure a lot of integrals converge, but they typically do, and then things work out there. So if these are nice, why am I talking about generalizing them? And that arises from understanding constant scalar curvature and extremal Poincaré-Type metrics and the limitations therein. So I will just talk about what I mean by extremal in particular. So the notion of the best Kähler metric on a given Kähler manifold, or even the best Hermitian metric on an Hermitian or complex manifold, might seem kind of silly to ask at first, but it actually makes sense for Riemann surfaces because of the uniformization theorem. So we can actually say, given a Riemann surface, pick the metric that has certain constant scalar curvature. And maybe that's not the best metric for your purposes at the time, but we can talk about canonical metrics there. And Calabi was interested in finding canonical metrics or a best choice of metric on other higher dimensional complex manifolds. In particular, given a choice of a Kähler class on a compact Kähler manifold, what's the best choice of metric in that Kähler class? And one answer is trying to find a Kähler-Einstein metric on a manifold, but there are very strong restrictions on whether or not your manifolds will even admit such a thing, because the first term class, or minus the first term class, needs to either be 0 or admit a Kähler metric. So Calabi sought to approach this from a different perspective, similar to the Yamabe problem in real Riemannian geometry. He sought to minimize the curvature essentially in a given Kähler class. So he constructed this functional called the Calabi functional, which you define on a given Kähler class. And the way I've written it here is by feeding a function in. That function will allow me to define all the other Kähler metrics in my Kähler class, starting from some base one. And I want to compute the L2 norm of the scalar curvature. So that involves computing the scalar curvature in its square and integrating against the volume form of this this new Kähler metric that you've chosen as well. And he sought to minimize this functional, which he actually showed. If you minimize the scalar curvatures L2 norm, then you'll actually end up minimizing the L2 norm of the Ricci and the Riemann curvatures as well. So something that minimizes this Calabi functional should be nice from a geometric viewpoint. And he dubbed the minimizers, or before they were shown to be minimizers necessarily, they were extrema of this functional. He dubbed them extremal scalar metrics. So we abbreviate that EXTK for extremal. And the Euler-Lagrange equation of this functional that such metrics will satisfy involves that fancy script D operator that I introduced earlier. So basically, a metric is extremal if its scalar curvature is in the kernel of this operator. But what that means is that the 1,0 part of the gradient of the scalar curvature is a holomorphic vector field. Another way of writing that is that the Lie derivative of the complex structure along the gradient of the scalar curvature is 0. So flowing the complex structure along this vector field does nothing. So this really outlines an interesting intimacy between the metric information of an extremal scalar metric and the automorphisms of our manifold X, because the holomorphic vector fields immediately show up in terms of defining or searching for these extremal metrics. So we get sort of this nesting of properties. We would like Kähler-Einstein, but it's pretty limited in which manifolds admit those. And I think a lot of people would suggest that constant scalar curvature is really the nicest thing outside of Kähler-Einstein, but there's also significant limitations on that. So we're going to be talking about extremal scalar metrics, which contain, of course, the constant scalar curvature and the Kähler-Einstein metrics, because they trivially satisfy this holomorphic condition. Okay, so a property of extremal metrics in the compact Kähler case that's going to fail for the Poincaré-Type case, as we've outlined, comes from Lebrun and Simonka. And it's sort of a general openness property for extremality. You'd phrase it a few different ways, but maybe the most concise one is given here. We have a compact Kähler manifold, then the set of Kähler classes which admit extremal metrics, that's going to rest inside of the space of all Kähler classes. It's actually an open set. So this condition of extremality is an open condition. It is not true in general that the property of being constant scalar curvature is an open condition. And it's certainly not true for Kähler-Einstein case, how strict the Kähler classes have to be chosen there. And there's a few different ways you can sort of think about this, but this openness condition in the extremal case is a very nice sort of natural property arising from an inverse function theorem argument using that script D operator that I defined earlier. Now, if your manifold X doesn't have any interesting holomorphic vector fields, if it doesn't have any holomorphic vector fields that are actually gradients of something, then you can't have any extremal metrics that aren't cscK. So in that case, you actually do get openness of cscK in this sort of degenerate situation. But in general, you're not going to get openness because you could perturb your constant scalar curvature class and land in an extremal class. And this is sort of the result that I'm working on to generalize. Can't be generalized to Poincaré-Type metrics, but hopefully can be generalized to the generalization that I'm about to share of Poincaré-Type metrics. So the reason this fails is the consequence of an obstruction provided by Auvray which outlines some rigidity of Poincaré-Type metrics, which is a little bit frustrating. If one is trying to establish a nice coherent theory of extremal complete Kähler metrics, not necessarily Poincaré-Type, then there's going to be certain things we would like from that, and the Poincaré-Type metrics are a little more restrictive. So the theorem Auvray shows is the sort of heredity condition on extremal and cscK metrics. So if we have an extremal or cscK Poincaré-Type metric on the complement of a divisor, complement of a hypersurface, then there's actually an extremal or respectively cscK metric on the hypersurface itself. So you're not going to be able to get an extremal metric, extremal Poincaré-Type metric off the hypersurface unless you actually have an extremal metric on the hypersurface. And if you have a, you're not going to be able to get a cscK Poincaré-Type metric off the hypersurface unless you actually have a cscK metric on the hypersurface in the specified Kähler class. And to illustrate why this causes a problem, I'll include this additional fact, which is quite handy in this setting, from Lars Martin Seknen. So from the get-go, we know that an extremal Kähler Poincaré-Type metric, what does it mean to be extremal? It means the scalar curvature is a holomorphic vector field. So it means we have some sort of a gradient holomorphic vector field on the complement of X, but it may have nothing to do with X itself. It may be some crazy vector field that doesn't have any extension across the hypersurface whatsoever. So there may be no decent relationship between vector fields on M less X and on M itself. But Seknen shows actually that if Z is the extremal vector field for a Poincaré-Type metric, so it's the gradient of the scalar curvature of this metric, then actually this has to extend as a holomorphic vector field across the hypersurface to all of them. So we can restrict our attention only to holomorphic vector fields on all of M itself and not worry about what may happen or what new things may be introduced when you cut out the hypersurface. So to point out why this is an issue, for one, it does seem a little bit rigid to only have these extremal or cscK Poincaré-Type metrics if your divisors or your hypersurfaces that you're working away from, if they don't have that. So that's already a little bit annoying, but we're going to lose this openness condition in the scenario I'll explain here. So the scenario we could have is our ambient manifold M. Let's say it doesn't have any automorphisms, but the hypersurface X actually does. And in particular, not just thinking about the automorphism group, but in terms of vector fields itself, this sort of factor H sub M is going to be the space of gradient holomorphic vector fields on M, and factor H sub X will be the space of gradient holomorphic vector fields on X. So we have no gradient holomorphic vector fields on M, but we do on X. So a whole lot more stuff happening on our hypersurface than on the ambient manifold. So if we start, we're thinking about this as an openness condition. So we want to perturb a nice cscK Poincaré-Type metric that we already have initially. So we're starting with omega in a class, what I defined above, which is cscK and Poincaré-Type. But if we perturb by a harmonic 1-1 form using the Hodge theory, that's how we're going to be able to illustrate changing the Kähler class just a little bit. If we perturb by some eta, then the resulting class when restricted to X, this may not admit any cscK metric. So we're starting at 1, but when you perturb, we may land in something that's extremal but not cscK on the hypersurface X. So if we do that, then the perturbed Poincaré-Type metric on M less X, that's not going to be able to be cscK, because if it were, then the restriction to X would be cscK. So it does feel a little contrived, I think, but at the same time, it's an issue that we don't have to deal with in the compact case. So that's what my generalization will try to handle. And sort of a half example to illustrate that. First, you would need to find an initial manifold X, which is compact Kähler, which has a cscK metric, but in all the directions you're perturbing that metric, you land at something extremal. I don't happen to know an example of a manifold like that, but the cscK property is not open, so such things should exist. And we can take the product with a Poincaré-Type manifold here given by the thrice punctured sphere, and that may have some vector fields, but it does have a cscK Poincaré-Type metric on it, and we can blow up points away from the subtracted points 0, 1, and infinity. This is actually due to Sekdan in the same paper that he proved the extension of the holomorphic vector fields. He proved that, actually proved how you would in general get an extremal metric on the blow up of a Poincaré-Type metric, but you don't need nearly as many hypotheses when you're starting with something that's cscK, thankfully. So you can rest assured that due to Sekdan, if we're blowing up a cscK Poincaré-Type manifold in the right way, then we're going to be able to get something that's also Poincaré-Type cscK. And if we blow up enough times, then we'll kill all the vector fields that are there on the ambient space. So not exactly a complete example, because I don't have a great example of a manifold X that has this property of always being destabilized from cscK to extremal, but this is how you would arrive perhaps at such a thing. And sort of the analytical issue of why this openness fails, and it doesn't fail in the compact case, is that this operator script D, when you include its adjoint, you get this fourth order differential operator called the Lich-Narovitz operator. And it's actually, it behaves quite well in its self-adjoint in the compact case, but the linear theory is a bit more complicated in the Poincaré-Type setting, because you're dealing with weighted weighted L2 spaces. And there's sort of extra elements that show up in the kernel that are not as well behaved. And these elements arise from the kernel of the Lich-Narovitz operator on the hypersurface itself. So that's why the hypersurface is causing us problems, because there are functions whose gradients are holomorphic on the hypersurface, but which are not arising from holomorphic vector fields on the ambient space. So that's where my generalization comes in, is to just include some distortion potentials, which they sort of end up ruining the Poincaré-Type asymptotics from the definition of a Poincaré-Type metric, but their linearization at the end, when we're trying to do sort of an implicit function theorem argument, they work out. So now I will discuss those generalizations. So one of the nice things that we have, we're starting with a cscK manifold X. That's our hypersurface. And this intimacy between the holomorphic vector fields and an extremal or cscK metric actually has important consequences for the space of vector fields. So due to Matsushima and Gnarled, the holomorphic vector fields, which I've written here is like your sections of the holomorphic tangent bundle, it splits into three spaces. You have the parallel vector fields, which, except for the zero vector field, they don't have any zeros. And then you have the Hamiltonian vector fields with respect to the symplectic form. And then you have the gradient vector fields. And a really interesting characterization, which I think is also due to Lebrun and Simonka, is that a holomorphic vector field is a gradient vector field if and only if it has a zero, which is quite interesting because whether or not a vector field has a zero has nothing to do with a metric. So the space of vector fields, which can be gradient vector fields on our manifold X, is independent of the metric, but the individual choices of what your vector fields will be and the potentials, which we call holomorphic potentials for holomorphic vector fields, that all depend on your metric. So this is all to say that we can actually choose holomorphic potentials in this unique setting of cscK compact. We can choose them such that they are real functions. So I'm going to choose a vector field V, which is the gradient of some function f sub V. And that means V lives in factor H. And as a vector field, it has a flow on X, which I will write as f sub tv, so for the time t flow of V. And then I can define a function psi sub tv according to this basic rule arising from the flow. So just an ordinary differential equation in psi sub tv. And this flow is a family of biholomorphisms because we're flowing along a holomorphic vector field. So it's actually going to preserve the Kähler class. So because it's a flow of a vector field, it would preserve the de Rham class anyway, but being a holomorphic flow, we're going to be preserving the Dolbeault class as well. So if we flow the metric, sigma, then it's going to differ from its initial value. So the pullback by sigma minus sigma, that's going to be DDC of some function. And you can show that by the way we've defined psi sub tv in green, this is actually going to satisfy this equation as well. And that's how I'm going to define this psi sub tv and point out its relationship to sigma. Okay, so with this function in mind, we're going to construct a local model that will present an alternative that is no longer obstructed the way that Auvray's obstruction illustrated for the Poincaré-Type case. The main method of proof that he used to show this hereditary property is actually that your Poincaré-Type metrics split into a sort of standard form of your cusp metric plus some extremal or cscK metric pulled up into a neighborhood. So that's sort of where that hereditary property is coming from. So local splitting, so we'll construct something that no longer is restricted in this way on a local model. So my local model will be the disk bundle in, where I'm just taking the trivial product of the disk with X, and I used in for neighborhood, and then I used in brev to sort of scoop out the zero section, and that's going to be the puncture disk across X. So that's sort of a local model for what's happening near X. And this has a projection map nu from our neighborhood to X. So here's where I'm going to introduce the word gnarl. Given a vector field that's in factor H, so it's a vector field which is a gradient vector field. The gnarl associated to this vector field and the metric sigma is the function capital psi sub b, which is the pullback through this log polar coordinate tau, which remember was log of minus log of mod z squared, times the projection map from our neighborhood. So psi sub tv has this real coordinate for the time tau, and then is a function on x otherwise. So we can pull that back, and that'll give us a function capital psi sub b, which is now defined on in brev, away from the zero section. And the fair question would be, why would I use a word like gnarl for this? And there are more readily available terms like twisted or warped, but those actually both already sort of mean different things in the literature, close enough to this subject that I thought a new term was significant and would be important to employ. So we have this new function on in brev. I can take DDC of that, and I can add it to my Poincaré-Type metric. That's going to give me something which is at least a closed 1-1 form on in brev. And this is what I'm going to be calling a gnarled metric, because we've taken our Poincaré-Type metric and we're adding DDC of the gnarl to it. So here are a bunch of facts about the gnarl. One thing that I probably should have mentioned is that this in brev up here is a product of the punctured disk and the cscK metric x. We actually have just the product metric is a cscK Poincaré-Type metric. We're using the cusp and just add the pullback of sigma, which means that by adding the gnarl to this, we get a gnarled Poincaré-Type metric. And if V is very large, then perhaps this 1-1 form is actually like not positive definite. But you can show that as long as V is small, then this form omega sub V is actually this is a symplectic form, so it defines a Kähler metric on in brev, and it's actually a complete metric going towards both, infinity towards the divisor, and then also towards the boundary. It's complete. And to show the completeness, actually, we don't need the fact that sigma was cscK. That doesn't really show up there. So that's true for any metric that you're pulling up from X, which is quite useful later. We also have this property arising from the group law of flows, which allow you to sort of apply the flow to the gnarl and move things around. So that's just handy for a lot of algebraic manipulations. And the other tool that's used is that we can extend the flow. So it's initially defined just on X, but we can extend it to in brev in a way that it actually generates a family of isometries for our gnarled metric. And the utility of that is we don't actually need to work with a whole weighted space argument. We can actually restrict all of our attention to a single compact slice of in brev. And yeah, the details of that are in my paper, but it means that it suffices to only look at distortion potentials on X, so phi in smooth functions on X, and in the end, we can restrict the scalar curvature to a slice in ImBrev and only worry about metrics whose scalar curvature restricts to a constant on that slice. We also have some rough asymptotics on the gnarl in that it behaves or grows exponentially, or at worst exponentially with respect to this log polar coordinate tau, where the epsilon k here definitely depends on the norm of v, but that's the only thing it depends upon. And yeah, the last fact I'll just be citing is that the linearization of the operator that takes the vector field to the gnarl is actually just a map that takes a holomorphic vector field to its holomorphic potential. So all those facts lined up for defining a gnarled Poincaré-Type metric allows me to state the main theorem. Basically, we have a neighborhood in the harmonic 1-1 forms, such that for every eta that's in that neighborhood, we can find a holomorphic vector field v sub eta that corresponds to it, and we can get a cscK gnarled Poincaré-Type metric omega tilde sub v sub eta, which is associated to this vector field, as well as a metric in the class sigma plus eta on the space in Brev. So this isn't true openness, because it would be nice to prove that if you start with a gnarled metric and you perturb, then you can get another gnarled metric if you have this sort of stability for gnarled metrics. But it shows that if we're starting at a cscK, then at least in this local case, if we perturb, we may not be able to get a cscK Poincaré-Type metric, but we will be able to get one which is gnarled. And just really quickly, the idea of the proof is just to write out a sort of modified scalar curvature operator. Takes in a vector field, takes in our form, and takes in a C4 alpha function. We take the scalar curvature of that thing and restrict it to just a single slice. And then the work is just showing that this map is actually C1, so that if we compute the derivative of the map in the v and phi directions at 0, the hope is that we'll get something that's invertible, so we can employ an implicit function argument, so that for small eta, we can always find a v and a phi that allow the cscK equation to be satisfied. And the way this works out is you just compute the linearization of the thing. If you've seen the linearization of the scalar curvature operator before, you'll notice the only additional piece here is we get this tau times fv that's arising from the linearization of the map that takes a vector field to its gnarl, and this tau times fv thing is precisely what was missing when those were the extra kernel elements in the kernel of the Legionnaire operator. So our gnarl was chosen so that its linearization would eventually allow us to get something that was surjective. And the surjectivity of this map is something that Seknen illustrated in his the same paper that I've cited already. So that allows you to prove the theorem, and a few extensions, directions that I'm currently working on for my thesis, and then hopefully we'll be able to continue working on afterwards. We can, I only defined all of this very locally, but we can throw a gnarl on this whole global picture on an entire m less x, just with an appropriate cutoff. You might lose some of the results that I showed, but you can at least define this thing and choose v small enough that you get a metric. But proving this result, like the openness statement that I had for the global picture, not just a local one, is more complicated because you're going to need to actually work with the weighted spaces in that situation, and you will kind of need to include an extension of the vector field from the hypersurface to the ambient space, at least locally. And when you're not a trivial product of the disk and the manifold, it's not immediately obvious what kind of extension you should use. There are options, but they work in different ways. That's something that I'm sorting with right now in order to try to prove a similar analogous results for the global construction of having a cscK Poincaré-Type metric on M less X and perturbing that way. Also, it'd be very interesting to generalize this to the normal crossings divisor case. That's sort of most of the Poincaré-Type results, especially that Auvray has done, involve working with normal crossings divisors. But you need to be careful about how you're talking about vector fields and things in that case. And then, as I alluded to earlier, it would be nice to get an actual genuine openness for these metrics, some sort of stability condition that gnarled metrics are just gnarled metrics essentially, and work that way. That would sort of be my dream for this setting, would be to have an extremal gnarled metric on the complement of divisor and show that that is actually the extremality is an open condition there when you perturb. So that would be something I'd like to do there. And then also the paper by Seknen, where he explores blowing up these Poincaré-Type extremal metrics. There's an important restriction involving the holomorphic vector field that you get as the gradient of the scalar curvature. And it would be interesting to see if these gnarled metrics could be used to sort of get away from that extra hypothesis that you need in order to preserve Poincaré extremality under a blow up. And one last comment, I think, is sort of about another direction one could go in. So there are other choices of flow that preserve the Kähler class. One of them is the gradient flow for the Calabi functional itself, so the Calabi flow, which I find this way using the DDC operator. So this preserves the Kähler class, which means that as you go along the flow, if you compare the flow with the starting metric, then they're going to differ by DDC of some function that's time dependent, and the Calabi flows, the potential here is given by this differential equation, and you could pull that back. So one could be interested in studying, trying to get a complete extremal metric on the complement of a hypersurface which doesn't have a cscK or extremal metric on it at all, but perhaps by sort of running the Calabi flow as you're getting closer and closer to it, you might sort of be able to improve the geometry to a point where it might work out. So you could do something analogous by creating a gnarl using a different flow like the Calabi flow to try to handle that case. Yeah, that'll be it.
Thank you so much. Thank you so much. Are there questions or remarks? Frédéric.
Yes, so just to be sure I understand the issue for this, say, generalizing Lebrun-Simanka. So you put yourself in the cscK setting, or it's really extremal ultimately for deformation?
So yeah, so it, the issue that I constructed is where the ambient manifold doesn't have any holomorphic vector fields. So you're only going to be able to have cscK there. So I'm sort of restricting to that case because
Okay.
there won't be any extremal. So
Oh.
you would want an openness of cscK in that case because there's no.
Okay, but the issue is that on the divisor there could be vector field, holomorphic vector field there that do not extend.
Right.
And then you want to have a deformation so that the deformation are cscK, right?
Yes.
But it's known otherwise you have deformation to get extremal metric in the Poincaré-Type setting?
No, I don't think that is known.
Okay. But so if you just want to do deformation for extremal metric, do you still need the gnarled this generalization of Poincaré-Type metric, or?
So I think you might, because it depends on when you change your class in the ambient manifold. The restriction that Seknan sort of introduces in the blow up problem is that when you blow up your manifold, you might end up the resulting blown up Kähler class might have an extremal vector field, which is not the original one when restricted to the hypersurface. And I think something similar could happen here, where if you perturb your Kähler class on the ambient manifold, you may change the extremal vector field of that Kähler class to one that is now different in a way that sort of disagrees with what you've done on the hypersurface. I haven't worked that out, but I think that is, I would expect that to arise, and the gnarl should take care of that.
And so this gnarled metric, they are they quasi-isometric to Poincaré-Type metric, or?
No, they're comparable in sort of an exponential way.
Oh, okay. But are they still finite volume or complete?
Yes. Yeah, they're complete and finite volume.
Okay. Thank you.
And in terms of stability, are there some kind of relationship that you could investigate with this gnarled cscK metric?
You mean like a case stability sort of thing?
I mean, yes. And what does happen also in the toric case? I mean, can you give a bit more some hints about what is happening in the toric case?
I am not sure what would happen in the toric case. I know that this is pure conjecture at this point, but I believe that Auvray, Seknan, and Apostolov were able to construct some complete extremal metrics on the complement of a divisor and Hirschberg surfaces, which were not Poincaré-Type. And they sort of showed this by basically pointing out that there were issues with a lot of there were conditions that needed to be satisfied using the toric construction for it to be Poincaré-Type, and they weren't satisfied. But they still had the metric there. I'm not suggesting that that was actually a gnarled metric or something, but it at least shows that Poincaré-Type doesn't satisfy every condition and isn't the end all be all. But no, I haven't worked out anything with the gnarl in the toric setting.
And for the stability, do you know if there is a kind of relationship with K stability, or is it?
No, I know that there are, in fact, I think there's a sort of a conjecture that's been modified, but a conjecture by my advisor, Sekedi, that would sort of involve a stability of a triple, where you have your ambient manifold and then your divisor and then a line bundle. And there are certain numerical constraints that are conjectured to need to be satisfied in order for that situation to admit cscK or cscK or extremal Poincaré-Type metric. And I haven't done any work on that, but it's possible that through a gnarled construction you might have weaker numerical constraints. I think that would be a bit of the hope of this gnarled construction, especially even going further and using different flows, is to create metrics that rely on the geometry of the hypersurface less, because we're removing the hypersurface. So it would be nice to have less reliance on the geometry of the hypersurface.
But there is no study in general of the kernel of the linear orbit operator related to cscK. Sorry, to cscK. Yes, Poincaré-Type matrix, right? Is it known this?
What was
The description of the kernel? I mean, a Fedor type alternative for the linear orbit operator, but associated to Poincaré.
Actually, SecNan has a lot regarding linear theory. Exactly, you know, with different weights, comparing L2 with Holder.
Okay, so you say there are something. Okay.
Yes, it's just not. Yeah, it's just more complicated because of these sort of extra.
Yeah, of course.
Yeah, but yeah, he has a lot of results on that in his paper on the blow up.
Okay, very interesting. Are there other comments or remarks from the audience? Oh, so it's time to thank our